Hi all, and welcome to the last SAEON Science Seminar for 2020. This week we have, or this month we've got Jenny Jackson-Veitch talking about ocean models. Jenny is a physical oceanographer working with Egagasini and working with Algoa and a numerical modeler. So I'm just going to hand it straight over to you, Jenny, if you want to share your screen.
Sure. I'm going to share my screen and hope I can get this right first time.
Just to remind you all to please stay muted with your video off just for connectivity's sake. If you have any questions, please pop them in the chat. If they're urgent questions, I'll interrupt Jenny and ask them. Otherwise, we'll save them for the end. So you can park questions for the end in the chat, and then we can ask Jenny them later. Cool. Over to you.
Thanks, Jasper. Are you seeing my slideshow in presentation mode?
Yeah, I can see.
Okay, great. So yeah, thank you all for tuning in this morning and welcome to my lounge. I'm going to take this opportunity to talk a little bit about South Africa's oceans, South Africa's turbulent oceans, but with a little bit of a focus on the Benguela system. So that's my sort of research focus. All of these names here are collaborators who are a motley crew of modelers, oceanographers, experts in satellite remote sensing. We have also people who go out to sea and take real live measurements. So a good place to start is by setting the scene. And this map of global sea surface temperatures does exactly that. So what we're seeing are warm sea surface temperatures at the equator in these shades of red. And towards the poles, we have blue cold water. Now, this north-south gradient in temperature is driven essentially by differential heating by the sun. And it's this differential heating and this gradient in temperature that pretty much drives all motion, both in the atmosphere and also the ocean. But now if we look a little bit closely at this picture, it's not just the meridional gradient in temperature that we see. We also start to see patterns emerging. You know, we've got these thin red ribbons on the east coasts of all continental boundaries. We have these blue bands along the west coasts of continental boundaries. And we also see these golden tongues that stretch westward across the equatorial Atlantic and Pacific. And these deviations from this north-south gradient in temperature are driven essentially by the fact that there are continents that also have these frictional boundaries, and also the fact that the Earth is rotating. So an object at the equator moves faster than an object at the poles. So these red ribbons here are what we call western boundary currents. They're fast, they're narrow, and they transport excess heat poleward. If it weren't for these currents, the equators would warm up more rapidly than the poles. Now, their importance to Earth's climate is big. They form part of the thermohaline circulation here, which basically moderates our climate by driving heat poleward. And it's this thermohaline circulation, and particularly the Gulf Stream, that became famous in a movie that was released in the early 2000s when apocalyptic movies were all the rage. So a short synopsis is scientists were monitoring the thermohaline circulation, and particularly the Gulf Stream, and they noticed that within the space of a few days, it slowed down so much so as to plunge the world into an ice age. Okay, so if you take away all the dramatic license and the Hollywood hype, this isn't entirely outside of the realm of possibility. So it is true that if the thermohaline circulation slowed down, our climate would be altered quite significantly, particularly with respect to this northward or poleward transport of heat. Unfortunately, this would not compensate for the vast amount of heating that is happening due to the excess carbon dioxide in the atmosphere. However, we still have to thank the ocean for moderating our climate. The ocean has absorbed huge amounts of excess heat, and it's able to do so because its heat capacity is so much higher than land surfaces. What that means is that the ocean takes a lot more energy to increase by 1 degree Celsius in temperature than land surfaces. So we have the ocean to thank for absorbing a lot of this excess heat. So our western boundary current in South Africa is the Agulhas Current, and it happens to be a very important part of the thermohaline circulation. It connects the Indian Ocean with the Atlantic Ocean. Now, while the western boundary currents are very popular and famous and sexy, all dressed in red, I'm going to be focusing on eastern boundary systems. So they are on the west coasts of land masses. They're characterized by cold surface waters. The currents are broad and sluggish and equatorward. The important thing about eastern boundary currents is that they're highly productive. So in this map of global chlorophyll, the greens are high chlorophyll, the reds are even higher chlorophyll values. Notice how each of the 4 major eastern boundary systems of the world, that is the California system, the Canary system, the Benguela system, and the Peru-Humboldt system, are characterized by higher chlorophyll, so higher productivity. Values in blue are where we're looking at ocean deserts. So the important thing about productivity is not only that it is essential for the marine ecosystem, fisheries, and food security, it also has a really big role to play in global climate. So, of course, when your nutrients come to the surface, photosynthesis absorbs carbon dioxide from the atmosphere. But as this organic matter decays and during respiration, of course, the carbon dioxide is released back into the atmosphere. So this is a cyclical process in pretty much most parts of the ocean, and in fact, land surfaces as well. But there are some really special parts of the ocean where the net effect is for carbon intake by the ocean. So there are parts of the ocean where carbon is absorbed into the ocean and sequestered. So the carbon is taken from the surface of the ocean and buried deep into the bottom of the ocean, where it basically stays and is removed from the carbon cycle. So this process of carbon sequestration has absorbed something like 25% of atmospheric carbon, and is another example of why the ocean is so important in moderating our climate. And this process of sequestration has the global ocean currents to thank. So actually another thing I wanted to point out about this figure here is that the land surfaces alongside eastern boundary upwelling systems are always dry. Okay, so that there always tend to be deserts. And this isn't a coincidence. So here we're looking at cloud cover over each of the 4 eastern boundary upwelling systems, and they're always associated with low-lying stratus clouds. This is because of the cold ocean surface temperatures that are conducive to this cloud type, which are not rain-bearing clouds. So this is another example of how the ocean drives not only global climate, but has a very big impact on local regional weather patterns. So the 4 major eastern boundary upwelling systems share many similarities, but the Benguela is quite different to all of them in that it is the only system in which a western boundary current directly interacts with an eastern boundary current system. So here I'm looking at a map of the surface eddy kinetic energy of the 4 systems. So what surface eddy kinetic energy does is really just tells us how turbulent the ocean is. So values in red means the ocean is much more turbulent. Colors in blue mean it's less turbulent. Notice how striking the Benguela system is. We've got this huge swath of high turbulence in this offshore part of the southern Benguela system. And a much lower turbulence or much more quiescent region on the shelf. This is quite different from the 4 other systems. And what is particularly striking is that the Benguela system is the only one that is plotted on a log scale, which means that the high values in the Benguela system are an order of magnitude higher than the high values in the other systems. And this happens to be quite a big deal for the Benguela system. So it's been on the cover of a number of international journals. And it has come to be known as the Cape Cauldron because it is so turbulent. So what I would like to do now is to give you a little tour of the Benguela upwelling system, which is essentially South Africa's sector of the Southeast Atlantic Ocean. So when I ask all of you to think about the Southeast Atlantic Ocean and what images it brings to your mind, it might be something like that. And that's fair enough if oceanography is not your thing. But for me, this is what comes to mind. This is one of my favorite schematics of the Benguela system. It shows us all of the major features. We've got the broad Benguela, it's quite tidy in this figure. So we've got a tidy Benguela current flowing northeastward. It is on the eastern edge of the subtropical gyre, which spans the whole South Atlantic Ocean. Just to the south of it, we have the subtropical front, where the South Atlantic Ocean meets the cold waters of the Southern Ocean. The Indian Ocean leaks over here as the Agulhas Current moves southward, and then it does a U-turn at the Agulhas retroflexion and turns back into the Indian Ocean. But before it does that, it leaks into the South Atlantic Ocean in the form of filaments, eddies, and here they represent the Agulhas rings, which are quite famous in that they are known to transport huge quantities of heat and salt into the Atlantic Ocean, and then it extends all the way into the North Atlantic Ocean, and in this way it contributes to the thermohaline circulation. So back to the Benguela. Close to the coast, we have a number of discrete upwelling cells, the Luderit cell being the biggest, and it's also the most perennial. We also note a number of intense shelf edge jets, which happen to be quite important. At the northern boundary, we've got the Angola Benguela front. This is where the southward flowing warm Angola current meets the Benguela upwelling system. And to the north of this, we have the Angola dome, which harbors low oxygen water because it is a retentive feature. So we end up with low oxygen water being produced there. So many of these features, especially the ones close to the coast, have been, our understanding of them is a result of decades of painstaking in situ measurements and analysis. But unfortunately, our understanding of the large-scale ocean only really improved with the advent of satellites a few decades ago. So the beauty of satellite information is that they provided large swaths of information at a regular interval. So we could have a much better understanding of the change within the system, but also how these large scale features move and how far they extend offshore. The problem with satellites is that they're not perfect, and a lot of processing goes into these images. So this happens to be a daily average from a very processed product. So this is a level 4 processed grist blended product. And we note that there's no data blanks. The information is also quite smoothed. But if we look at the same image from a different product that is not as processed, we note that there, in fact, is really often cloud covering most of the region. So the problem with satellite information is that a lot of the information that we get is highly processed, and we lose a lot of the key features of the system, particularly when we have a system that has a lot of intense fronts. So where the temperature changes rapidly in space, the processing procedures think that it's a problem and they flag that information. So we end up losing information, particularly near the coast in the Benguela system. But models can fill this gap. So here is a plot of sea surface temperature and currents from a model, and immediately we notice things that we weren't seeing with satellite information. We've got these very distinct upwelling plumes off Cape Columbine, for instance, very intense fronts, especially close to the coast, and these very fine scale twirling, swirling filaments that extend quite far offshore. The beauty about models as well is that they have revealed to us that the ocean has all these fine scale features that we don't capture in satellites, but that these features also move rapidly. So models capture and they fill the gaps, not just in space, but in time. So I'd like to go back to my tour of the Benguela system. So at the front door, let's call the northern boundary the front door of our system. We've got the Angola-Benguela front. And this, like I said, is where the warm and tropical Angola current meets the cool waters of the Benguela upwelling system. It manifests as a very intense meridional sea surface temperature front. And the importance of this front is the fact that it keeps the tropical waters of the Angola, which often tend to be low in oxygen because of this retentive region here, they keep these waters at bay. They keep them from entering the Benguela system and impacting the marine ecosystem there. This plot here is a Hofmüller plot. Many of you might not be aware of how these plots work, but on the y-axis, we're looking at latitude from about 12 degrees-ish south to 34 degrees south. On the x-axis, we have months. So these are average months of the average year. This is a climatology. And the plot is of sea surface temperatures based on satellite. We can very clearly see that there's a distinct seasonal cycle in the Angola-Benguela front. And this seasonal cycle is related to the seasonality of the northern Benguela upwelling system, which is driven by the local alongshore winds, but also by the large-scale winds that drive the Angola current. So while the Angola current does not seem to penetrate this Benguela system at the surface, models have shown us that in fact it does enter the Benguela system at depth. So what we're looking at here are alongshore velocities at the shelf edge. So in the northern Benguela, the shelf is relatively narrow. The shelf edge is more or less here. I hope you can see my cursor. So anyway, these currents are the alongshore velocities at the shelf edge. And what we're seeing is that beneath the surface, the Angola current does actually penetrate southward into the northern Benguela system, but only as far as about Luderitz, where everything abruptly veers offshore. This is good news for the southern Benguela system, meaning that we don't have a source of external low oxygen water coming onto our shelf in the southern Benguela system. However, for the northern Benguela system, we've got this introduction of low oxygen water on their shelf, which tends to prime it for sulfur eruptions. Okay, so sulfur eruptions happen when the oxygen levels are so low in your water column that anaerobic bacteria start to oxidize organic matter using the sulfate ion instead of oxygen. This generates or forms hydrogen sulfate, which eventually accumulates on the ocean floor, and at some point it outgasses and rises to the surface in what we call sulfur plumes. And and we can see these from satellite. Okay, so the northern Benguela system is subject to frequent low oxygen events and sulfur plumes because it doesn't only have low oxygen water that is locally produced, but also it has this source of external low oxygen water, which is not the case in the southern Benguela. Luckily for us, because this current moves offshore at Luderitz. Right, so this Angola current actually every few years, typically it's a decadal cycle, 5 to 10 years, it extends much further into the northern Benguela system, producing fairly extreme anomalies that you can see here and here and here and here as these red blobs in the northern Benguela system. Now, when these anomalies persist for 2 to 3 months and are greater than about 3 degrees Celsius, they are called Benguela Nino events. So Benguela Nino events arise due to wind anomalies in the tropical central to western Atlantic. These wind anomalies energize the ocean and send a Kelvin wave across the equator that then sends its energy southward along the African continent. And in doing so, it pushes the Angola current further south into the Benguela system. These events are important because they impact the marine ecosystem, particularly in the Angolan and Namibian part of the Benguela system, but they also cause heavy rainfall in parts of Angola as well as Namibia. So what about the southern boundary? So our southern boundary is open pretty much to the Agulhas Current, which enters as a mishmash of eddies and rings and filaments and plumes. And it generates this area of extreme turbulence, as I've described before. So we end up with this blob of highly turbulent water, which tends to be very much confined to the region south of the Walvis Ridge over here and offshore of the shelf edge. This is the Cape Basin, and it's also been known as the Cape Cauldron. So this is just the surface eddy kinetic energy, but what's happening with depth? And the beautiful thing about models is that we can see what's happening at depth. So in this plot on the left here of eddy kinetic energy, I've averaged the EKE from the surface to the bottom. The picture looks relatively similar in that the Cape Basin once again shows up as a region of very high turbulence, but we're also seeing a region of turbulence right on our shelf edge, as well as close to the coast. And this is related to nearshore upwelling processes and the intense upwelling jet there. So these depth averaged eddy kinetic energies are derived from this numerical model, which is a ROMS model. It's a two-way nested model. So we have a parent domain at a lower resolution, which forces a high resolution child domain. Now, if I were to plot lines of constant surface flow, which I show here in these white lines, where the white lines are close together, the current is fastest, right? So in a way, we can think of these white lines as the mean Benguela current, the mean surface Benguela current. We note that the current meanders quite intensely, but also it tends to be fastest and meanders most where the eddy kinetic energy is highest. Okay, so my next question was, well, how is this related to the passage of Agulhas rings? Okay, remember I spoke about those Agulhas rings that are shed at the Agulhas retroflexion, and they move upward into the South Atlantic Ocean. Well, if I add all the paths of all Agulhas rings that have passed this area in the model for the past few years, that path is exactly in the same place as that meandering Benguela current and the region of very high kinetic energy. So this is suggesting to me that actually the Benguela current is very much related to this passage of Agulhas rings. So my next idea then was to remove the Agulhas current from my model and to see what happens. And this is exactly what I did. So I built a dam wall of Durban, approximately, which caused the Agulhas current to retroflect very early and not to directly impact the Benguela system at all. And the response of the Benguela was, firstly, of course, we have no Agulhas rings. So all those black dots were removed. What happened to the mean surface current? Well, not surprisingly, it reduced in strength and intensity quite significantly. And it's not as meandering either. And also, the eddy kinetic energy reduced significantly. And the highest eddy kinetic energy we see here is related now to the fact that the subtropical front has been extended northward. So what this little animated sequence has told me is that actually the apparent mean meandering of the surface Benguela current is simply a manifestation of the passage of these Agulhas rings. So what we see in the mean state, you should always question, you know, the mean state is often a little bit of a fiction when you're using a highly turbulent ocean to create that mean. Right, so that's what's happening at the surface. What about the Benguela system at depth? So here is a plot of basically the volume flow of the Benguela system. So what you do is you integrate the currents from the surface to the bottom, and you create these streamlines of flow. So we're looking, each streamline represents a volume transport, a constant volume transport. And again, where those lines are close together, we have the most intense volume flow. The first very striking thing about this picture is that in the northern Benguela system, we have a very weak cyclonic, large-scale cyclonic circulation, poleward flow along the shelf, and a very distinct offshore flow at Luderitz. This is very different from the picture in the southern Benguela, which shows very much more meandering and much more intense northwestward flow. This is, of course, the mean Benguela current that is impacted by these passing Agulhas rings. Now, I was very interested to know what was forcing this volume flow of the Benguela system, so the surface to bottom volume flow of the whole Benguela system. And the very neat thing about geophysical fluid dynamics and oceanography is that the theory has taught us a few tricks. So the trick that I'm going to use here is this Sverdrup relationship. So the Sverdrup relationship tells us that if your flow is very large scale and small scale processes are not important, then you can use just the surface wind stress and the fact that the Coriolis force changes with latitude to derive this exact plot. Okay. So if the Sverdrup relationship is true, then I should be able to recreate this plot exactly using theory. And this is exactly what I did. So here's the Sverdrup relationship, right? It tells us that the surface wind stress and the change in Coriolis with latitude drives the meridional flow, meridional volume flow. And this is what I got. Okay, so on the right, we have the theory, and on the left, we have the model results. Note that in the northern Benguela, the Sverdrup relationship and the theory holds really well. Okay, so what we can say is that in the northern Benguela, the large-scale flow is driven purely by the wind stress and the change of Coriolis with latitude. This is a really awesome result if you think about it. So what it tells us is that just the surface winds can tell us what the ocean flow from the surface to 4,000 meters deep is doing, which is incredible. But in the southern Benguela system, this relationship definitely doesn't hold. We're not getting this intense, mean, meandering volume transport at all. So what that tells us is that in the southern Benguela system, small-scale features and eddies are really important, and we can't ignore them. Large-scale theory doesn't hold there. So if I were to respectfully edit my favorite schematic, I would do this. I would make the surface flow much more meandering, not as tidy. I would include the depth integrated flow, which is quite disparate in the northern and the southern Benguela system. We've got this weak cyclonic flow in the north versus this strong meandering flow in the southern Benguela system. And I would also include this deepening poleward undercurrent that is really important for the import of low oxygen water onto the northern Benguela shelf. So moving into the real crux of the Benguela system, the coastal upwelling. So coastal upwelling is what drives the high productivity in upwelling systems. And it's pretty much a linear process. So we have strong winds. Here's a Hoffmuller plot of the wind stress that drive upwelling fluxes. The alongshore winds pushing the surface waters offshore, causing deep, cold, and nutrient-rich water to rise to the surface. These plots look pretty much the same. The alongshore wind stress matches the upwelling fluxes. It is a linear process. The thing is, productivity does not only depend on rates of upwelling, it also requires that the nutrients are retained within a certain location. It requires that we have transport of fish eggs and larvae into a place where they can be recruited, where they can develop. So a very important feature in the southern Benguela system is the Benguela jet. So its importance lies in the fact that it transports fish, eggs and larvae from their spawning area on the Agulhas bank into St. Bay, which is relatively protected, and it's their nursery area. It was initially anticipated by Bang and Andrews in the 70s, I think, because of the very intense cross-shelf temperature gradient. We've got cold temperatures at the coast, very warm temperatures offshore that drive northwards current. Okay, so eventually they measured it, and it was the order of 50 to 75 centimeters per second, which is really strong for Eastern Boundary System standards. More recent measurements have shown it to be there still, and it's still a very persistent feature. It tends to belong, or it tends to live between the 200 and 500 meter isobats. Here it is, this big red lens of water. But further offshore, a very valuable ADCP measurement has shown that it's quite variable. I mean, it's there, it's pretty much always there, but there is some variation. The problem with these golden in situ measurements, that as valuable as they are, they don't tell us the full story. So I turned once again to my spatially and temporally coherent model to understand this jet better. Here is a plot of the model jet. We're looking at model speed and direction here. In the yellow colors, we see the intensified jet current off Cape Columbine and Cape Point. But we see that in the model, again, the jet is seated between the 200 and the 500 meter isobats, which is exactly where we expect to see it. Now, if I put lines of constant sea surface temperature, we note very distinctly that this jet sits in a place where the cross-shelf temperature gradient is very intense. And this temperature gradient is amplified by the warm waters of the Agulhas Current coming in this offshore part of the system, and the cool upwelling regime at the coast. And if we were to remove the Agulhas, we note that this jet is reduced significantly and contracts towards the coast, and is really just a response to the coastal upwelling close to the coast. So I wanted to dig a little bit deeper with this temperature gradient between the 200 and the 500 meter isobats. And the beauty about models is that you have all the information you need at your fingertips. You have every single term of every equation that you can use. So I wanted to look at the heat budget equation. I wanted to look at every term, or no, I actually just looked at the horizontal heat advection term. That is the term that describes how the horizontal movement of water leads to heating in the system. So I looked at this term all along this section from the coast to some distance offshore. And I wanted to find out what is it exactly that is driving this intense gradient between the 200 and 500 meter isobats where the jet sits. So here's my graph. Our x-axis is ocean depths. Here's our 200 and 500 meter isobats. This is where we expect our jet to reside. On the y-axis, we have heat flux. Positive values refer to warming, negative values cooling. So I'm going to start with a baseline of no Agulhas. Okay, so if we had no Agulhas, like in other eastern boundary systems, the net effect, the total effect of the heat flux is for cooling. Okay, so we're at an upwelling system. It's not surprising that we have most cooling close to the coast. This cooling reduces somewhat offshore as the water is advected offshore. But as you go even further offshore, we end up with slightly more cooling. But this is just due to the fact that the subtropical front is moving upward into our system. Okay, so that result isn't very surprising. I was also interested to know, well, how much of this cooling is related to eddies and how much of it is related to the mean state. And when I talk about eddies, I don't just talk about coherent cyclonic or anticyclonic eddy. I talk about turbulence in general. So when I separate this term into its mean and its eddy counterpart, it's very clear that it's really just the mean state that drives this cooling. Turbulence is really not important. So what happens when we turn on the Agulhas? Well, the picture looks quite different. The total warming along the section shows that we have a net cooling close to the coast, which is much greater at the coast due to the coastal upwelling. The cooling continues until about the 300-meter depth level, at which point we enter a regime of warming. Okay, so the fact that between the 200 and the 500-meter isobats, we have cooling on one side and warming on the other side drives this very intense temperature gradient between those two isobats, and therefore it drives the intense jet current. Now again, separating this total heat flux term into its mean and its eddy counterpart, we note that close to the coast, the mean component dominates. This is just your seasonal, regular upwelling cycle. But as we move offshore, our eddy term becomes much more important. So what this has told me is that the intense cross-shelf thermal gradient is driven by, firstly, the highly variable warming by the Agulhas Current in the offshore part of the system, and the much more regular seasonal cooling by upwelling at the coast. Right. So the Benguela jet is important, and recently Mohabo graduated with her PhD, and she showed that indeed the Benguela jet is very important for the transport and fish larvae into St. Helena Bay. She showed that there was a direct correlation between transport success and Benguela jet strength anomalies. The Benguela jet has also been implicated in the transport of harmful algal blooms, and believe it or not, the theft of a surfboard. So transport is very important in the system, and the Benguela jet is important. Another thing that is essential for productivity in the southern Benguela system is retention. So just to drive this home, here's a very nice plot of the marks. It's an old one, 2007. We're looking, they're Hofmuller plots again. We're looking at, on the y-axis, latitude from about 12 degrees to 34 degrees south. X-axis of all these separate plots are the mean monthly conditions. So I'd like you to focus just on the wind stress and the chlorophyll index. So remember, wind stress is pretty much a direct proxy for upwelling fluxes. Note that at Luderitz, we always have high wind stress and therefore high upwelling, but always low productivity. And this is because there's very little retention at Luderitz. The water upwells and is evicted offshore immediately. The nutrients don't have time to photosynthesize and become productive. So again, I go back to my models, and I'm interested to know how the Agulhas impacts retention on the southern Benguela shelf. So as the reference, I use my model that has the Agulhas current in it. Notice the very strong jet current over here. We've got large eddies and turbulence in the offshore part of the system. I seed this model with particles in the southern Benguela system. The color bar just relates to the depth of the water. I do exactly the same for a model that has no Agulhas in it. And the currents immediately look quite different. We don't have as strong a jet current over here, and the turbulence in the southern Benguela is much lower. So what happens if we play this forward? Well, let's have a look at what happens to the particles. So notice how for the reference experiment on the left, the particles tend to move along the coast, whereas for the no Agulhas experiment, they immediately start moving offshore. So what these results are showing us is that the Agulhas current has a pretty important role to play in retention on the southern Benguela shelf by producing this intense jet current at the shelf edge that serves as a kind of barrier to the cross-shelf transport of these particles. So these particles might be nutrients, they might be larvae or fish eggs or whatever. Okay, so finally, I would add to this lovely schematic is an important zone of retention on the southern Benguela shelf here. Also note that retention is important not just for productivity, but it also has implications for low oxygen water. So the more retentive a region is in the ocean, the more likely it is to become hypoxic. Right, so now that I've mutated my favorite schematic a lot, I think I'm going to move on, and I would like to just talk a little bit about what's happening in my corner of SAEON. So what I'm currently working on is the SAMISANA project, which is the Sustainable Ocean Modeling Initiative, a South African approach. I have it on good authority that SAMISANA means something like to work together in Sepedi. And the idea behind SAMISANA is to develop and sustain an operational ocean current forecast system for South Africa's exclusive economic zone, and to do so in a transformative fashion. So that is the official vision. But to get there, we have a lot of work to do because we don't have enough capacity. So a lot of my work is in capacity development, which is supervising students in modeling projects. And the other side of what I'm doing in conjunction with Matt Carr, Christina Russo, and Giles Ferron is to develop demonstration products, operational products that will eventually feed into the Ocean and Coastal Information Management System. This, by the way, is a joint DEF and SAEON initiative. So I took some very quick screen grabs yesterday on a test web server that Matt Carr and Christina Russo have developed that demonstrates how we have added value to existing global model and satellite products. So Christina has developed an algorithm to locate the Agulhas Current core, as well as its edges. And these have been operationalized and are disseminated on this test server, which you can have a look at. Here's the website. She's also got sections of velocity and transport of the Agulhas currents. Matt has identified cyclonic and anticyclonic eddies operationally using model. And satellite information has provided us with the means to add sea surface temperature anomalies operationally as well to this website. We've also got a really cool marine heat wave tracker, which is also operational. So please go check these out. There are some really cool things here. So moving on to models. So while we have been using global models, they are at a fairly low resolution. So this isn't conducive to a lot of the stuff that we need the models for. So what I am working on is developing an optimized high-resolution hindcast, or a historical model of South Africa's entire exclusive economic zone. I'm not going to go into details of the model because that's probably too much information, but the importance of this is that it is on the critical path to developing a full forecast model of our exclusive economic zone, which is more or less that. I haven't included Marion's exclusive economic zone. But also it allows us to monitor is probably the wrong word, but it allows us to investigate long-term trends and changes within the system. And it can also be used for various research and training objectives, which is fantastic. A more exciting part of what we're doing, I think, is a forecast model that Giles Ferron has implemented for Algoa Bay. It is very fresh. This little GIF was swiped about a month ago, and it shows us 3 to 5 day forecasts of the ocean currents and temperatures, which is great. Algoa Bay is a very contentious region because of the oil bunkering that happens there, in conjunction with the fact that there are a number of MPAs and important bird colonies. Just last year, there was an oil spill. It wasn't big, thankfully, but hundreds of birds were impacted. we were contacted by Integrated Coastal Management at that time to assist with the cleanup. Unfortunately, at the time, we didn't have any high resolution forecast models. We had to make do with what was available globally, which isn't sufficient in this tiny bay. So this is what has inspired us to use Algoa Bay as our pilot site for our forecast. And by the end of this financial year, so by March, we will be coupling this model to an oil spill tracker so that we can operationally see, you know, if there was a hypothetical oil spill within either of these oil bunkering regions, where would it end up and how quickly would we have to get to these islands to mitigate the impact. So that's me, and I realize I've said quite a little about a lot of things, but I only have two take-home messages. And the first one is, your biome really needs the ocean. It helps to moderate global climate, but also it drives local weather patterns. And secondly, numerical models are really awesome. We can use them in innovative ways, not only in experimental and more academic projects, but also operationally. And that is all. Thank you.
Great, thanks, Jenny. Yeah, covered a lot of ground there. Lots of pretty figures, but I wasn't quite sure that I followed everything, but I tried. Yeah, I don't know. If anyone has any questions, feel free to raise your hand or pop it in the question box. I see we've got one from Zach, who asks, does the Benguela Current affect the Agulhas Current?
That's a great question, Zach. Being a Benguela person, I would like to say yes, but I don't think so. I don't think so. I don't think the Benguela, no, I don't think so. It's a good question.
Kind of directional, I suppose.
Yeah, exactly. Perhaps indirectly via, yeah, I don't know. Maybe we should put a student on it.
Yeah. Ooh, Zach's just hit me with a big follow-up question. Hang on. So I'll just read it out to everyone. Jenny, you might want to read it separately. And then, so he says, I've heard that the gas find with Mossel Bay would require deep sea drilling and that this is difficult because of the Agulhas Current. Is this in any way related to the turbulence you mentioned from the eastern boundary meeting? Or is it just that the Agulhas Current is a fast current? Are these systems relevant to something like deep sea drilling? And if so, do Total and the likes use this research?
Another really good question. So yes, I mean, the deep sea drilling is very problematic, and we have spoken to Total and they've actually given us data. So we're pleased about that. They really struggle with the deep sea drilling because it's an extremely turbulent region, not because it's related to the Benguela as such, but just.
Oh, I think we've lost Jenny.
Oh.
Oh, no, you're back.
Oh,
So you just broke up there for a second. You had your hands up and you said.
Like a pose. Yeah, so it's a really turbulent region and they are very desperate for good forecasts so that they can remove their rig, you know, before an eddy or a highly turbulent feature gets in the way of their operation. So they are desperate for more information and forecasts, good forecasts in that region. My worry is that, you know, they're only exploring. What happens when they actually start drilling? You know, they're going to have their system and their forecasts really, really well thought out before then. Thanks, Zach, for that, that thought.
Your hand's taking us in another direction.
I see. So.
Yeah, do you want to answer that? Okay. What are the forecasts for El Nino this season?
Yeah, so Johan, I believe it's a La Nina, and I can attest to that because during La Ninas we're supposed to have stronger winds, and today is hellish windy in Cape Town. So I believe it's a La Nina.
Yeah. Laura's asking about how well the models plot out the deeper currents I think she wants to know about the benthos and the benthic biota
Yes,
in particular.
yeah, things at the very bottom of the sea. So Lara, that I need in situ information. I love models and I will sing the praises of models any day, but you know, in situ information is golden. So if the more information we have about actual currents on the seabed, the more I could actually answer that question. But for now, I really don't know. We have currents. I don't know if they're right.
Yeah.
Mm.
So I've got a question more about my biome, or maybe linked to my biome. So during the glacial periods, the Agulhas Shelf is meant to have been exposed. And I was wondering what that did to the currents and the interaction, or if that's been explored at all, because that's on the kind of 10 to 12,000 year scale, and we're dealing with a biota, in both the marine biota and the terrestrial biota, that's obviously a lot older than that. So it'd be interesting to know how that perturbs things.
I love this stuff. I just love paleoceanography and the idea of how the whole system connects. And I remember George Philander, when he was here a long time ago, he was on this bandwagon of connecting fynbos with oceanography.
Yeah.
So I think there's something in it. But I think, you know, if the ocean had sort of receded, revealing more of the shelf, I expect you still would have had an eastern boundary current and a western boundary current. You know, the earth is still rotating. We still have the same gradient, but yeah, I don't know, we could run a hypothetical model and see what happens. Yeah,
I mean, I wonder in a way to what extent the kind of like local current systems would alter, either exacerbate or buffer the climate, the broader climate signal of the glacial period. This would be what I'm interested in. Like, I'm not an expert in this space at all, but it's this thing of plus 1.5 degrees doesn't mean everywhere. It's different everywhere, and I'd be really interested to know what the local effects of local currents would be.
It is really, it's a very interesting topic, and there has been some work done on what happens when our westerly wind belt shifted, and what happened to the Agulhas, and then what happened to the global thermohaline circulation. So there is some work being done on it, and it's incredibly fascinating. And I would love to go there.
Cool. I'm just trying to catch up on the. So Lara is keen to work on the benthos, and Juliet wants you to run a model without the Benguela.
I'd be happy without the Benguela. No way. You run your own model without the Benguela.
I was about to say, it sounds like go and score goals for another team.
Yeah, exactly.
Cool. Well, thanks, Jenny. I think unless you have anything to add, it seems like there aren't any more questions right now.
Cool.
I suppose I had one more, which is more of a national pride one. It seems like Australia don't have a major eastern boundary current.
Well, they've got the East Australian current.
Yeah. But it's not considered a major eastern boundary.
No, it doesn't have a nice little red ribbon.
We'll have to remind them that as often as we can.
It's still warm and it's still relatively fast, so just be careful at how you go about it.
Oh, we've got some late breaking questions. Zach wants to know if there's a simple way to download the data sets and the model that the models use, and he wants to play around with charting and visualizing this for some of the work he's doing with Awazi.
Sounds great, Zach.
Yeah.
So there is some model data from one of my colleagues, collaborators, on our server, and it's on a thread server, which is fantastic. It makes it very easy to download and subset. So I can send you the link if you like to that.
Is that something I could share more generally?
Yes, of course.
So maybe if you send it to me and then I'll send it out.
To you. Yeah. Okay.
Cool. Thank you very much. And thanks all for attending. It was a good crowd, lots of good questions. And feel free to contact Jenny directly afterwards if you, otherwise email me and I can put you in touch if you can't find her email address or the like. And we shall see you again in January for our next presentation, which I need to just double confirm before I advertise. Cool.
Thanks, Jackson. Thanks, everyone.
Cheers.